Hello everyone, my name is Paul Albert. I'm going to present to you today our paper, which is titled "Is Your Noise Correction Noisy?" The name of the algorithm we propose in this paper is PLS for pseudo-label selection, and we tackle here label noise in image datasets. My co-authors are Arazo, Tarun, Krishna, Noel O and Kevin McGuinness. We are from the Dublin City University in Ireland. So what's the problem statement here? What do we tackle in our paper? Well, we aim to design algorithms that are robust to image datasets that have not been curated for image classification. And this would typically imply that when you create your dataset, you're going to use a search engine to retrieve images that would be examples of your classes from the web. And you don't spend time asking humans to make sure that all the retrieved images are correctly assigned to the category and are relevant to your classification task. So this means that you end up with two different types of noise. The first one, which are out-of-sample images, so images that would a priori not be relevant to your classification task because they do not contain any of the elements you're interested in learning to classify. And the other ones are ambiguous images, where it's not clear that these images are actually relevant. They could be hard images or images where you're not actually sure that they belong to the class you want to learn to classify. So these are images that are underlined in orange here in this example. So what is our contribution? What do we do different from existing algorithms? Well, in this paper, we propose to focus not so much on the detection of noisy images, which is something that's extensively done in the literature, but more what do we do once images have been identified as noisy. A typical approach in the literature that's insufficient in our opinion is that once the image is detected as noisy, a pseudo-label or a true label guess is going to be performed on the image to guess the actual true label of the image, and this pseudo-label is going to be used to minimize the classification objective using an updated label. In our case, we propose to make sure that once we output this guess of a pseudo-label, that the pseudo-label is actually going to be correctly matched to the image, or at least is going to be confidently predicted by the network. And we don't use confidence on the prediction directly, but we use another metric that we found to be superior, which we call the pseudo-loss, and I'll talk to you about this now. So the pseudo-loss is a very simple term, is simply computing the cross-entropy between the pseudo-label that you output for an image, which you're not sure is going to be correct or not, and a prediction on an unaugmented view of the same image. So the pseudo-label here is guessed using a consistency regularization approach, so simply an average of the prediction of the network on weakly augmented views of an image. So we found this metric to be very well correlated to the correctness of a pseudo-label, and specifically we observed two modes in this loss when evaluated over all the noisy images, where the low loss mode is going to be the mode where the pseudo-label tends to be correct, and the high loss mode where the pseudo-label will tend to be incorrect. We can then retrieve each of the modes using a mixture model, in our case a Gaussian mixture. We do also much more in the paper. Specifically, we propose a contrastive objective that we use to regularize the classification objective, which is an interpolation between supervised contrastive and unsupervised contrastive. So unsupervised contrastive being used for the out-of-sample images. We have state-of-the-art results on various datasets. We also have an ablation study if you're interested in seeing what's the importance of every component. And all this is in our poster, so come at our poster session. I'll be happy to discuss the paper more. Thank you.